Hello students, Assalamu alaikum. Welcome to the Electrical Engineering channel. In this lecture, I will discuss the last test which is famous for DC machines, and this test is applicable on series wound DC machines. And in this test, two identical motors are coupled, right? And or we can say two identical machines are coupled. One machine runs as motor and the other machine runs as a generator, and this is the circuit diagram which is required for this test. And you can see this is the field winding of the motor, this is the armature winding of the motor, and V1 reads the input voltage of the motor. We will connect an ampere meter I1 over here. This is the input voltage supply, and what we will do different for this test is that the field winding of the generator will be connected in series with the motor circuit, right? So this is the motor circuit in which the field winding and armature winding of the motor are connected in series. And the third winding, which is the field winding of the generator, will also be connected in series in the motor section. And after that, we will have the armature winding of the generator, and this armature will be coupled to this motor. So when motor runs, it will run the generator. The only difference is that the field winding of the generator will be connected in the motor circuit in series with the motor circuit, but it won't do any operational problem because this field winding of the generator will produce magnetic flux. And when this generator has magnetic flux, and when this generator also receives the mechanical energy, it will produce the electrical energy or the induced EMF. So this is the generator side, and we will have an ampere meter connected in series with the armature winding of this generator, and this is a voltmeter which is used to measure the voltage of this generator. And here we will have a variable resistance. So the FG field winding of the generator is connected in series with the motor so that same current flows through FM. So same current which is flowing through the field winding of the motor will be flowing through the field winding of this generator, and iron losses are same, right? When the current is same, the flux will be same, and when the flux is same, the iron losses or core losses will be same. R is varied till motor reaches its full load current, right? So R is the load of the generator. When we decrease this R1, the output of the generator will increase, right? So when output of the generator increases, the output of the motor will also has to increase, right? So in that case, the input power of the motor will also increase. So this is how this system works. And the input power of the whole system is equal to V times I1. V is the applied voltage, I1 is the input current, and the output current of the system is equal to V2 I2. This is the overall output, which is equal to V2 into I2. And WT are the total losses, and these total losses are equal to input minus output. So this is input and this is output. And copper losses, and the uh, total copper losses in the motor side are equal to the armature copper loss in the motor and field copper loss in the motor section, right? So field copper loss is equal to this is actually Rm and this is Rg. Both are equal, right? So the field winding resistance of this motor section and the field winding resistance of this generator section are equal. So 2Rf plus Ra, right? So 2Rf plus Ra times I1 square. So these are the total copper losses in the motor side, armature plus field. And these are the armature copper loss at the generator side. This is the armature resistance and this is the armature current of the generator. Similarly, stray losses are equal to total losses minus the copper losses, right? Total losses minus copper losses are equal to the stray losses, and stray loss per machine are equal to uh, total stray losses by 2, right? WT minus W copper divided by 2. These are the stray losses per machine. Now we will calculate the motor efficiency. This is the input power of the motor, which is equal to V1 I1. So here you can see this is V1, right? So V1 is the voltage across this motor, voltage across only this motor is equal to V1. This total voltage is equal to V, but this is V1. So this is the input power of the motor, and losses in the motor are equal to the copper losses plus stray losses, and these losses are equal to Ra plus Rf into I1 square plus Ws, and that is equal to Wm. Here you can observe that we won't include the field copper loss of the generator, right? So only the field winding of the motor side will be considered. So Ra plus Rf into I1 square plus Ws, that will be equal to Wm, motor losses. And this is the input power of the motor. So efficiency of the motor will be equal to input power minus losses of the motor divided by the input power. Now we can calculate the efficiency of the generator, and for this we will take the expression of output power of the generator, that is equal to V2 I2. Now the copper losses of the generator side will be equal to I2 square Ra. This is the armature copper loss of the generator, and this is the field copper loss. And from the field winding of the generator, I1 current is flowing, right? This is the field winding of the generator, and I1 current is flowing through this field winding. So we will use I1 square Rf. Now Wg, which is actually the losses in the generator, these are equal to copper losses plus stray losses, and that is equal to Wg. Now the efficiency of the generator can be evaluated by P out over P in. This is P out, and P in is equal to P out plus losses. So this is how we can calculate the efficiencies of motor and generator by performing the fields test, and this test is valid for the series motors, right? This is specific only for the series motors. And the reason why we have connected the field winding of the generator to this motor side is that we wanted the stray losses across both the machines to be equal. If the stray losses of both machines are equal, then we can use this expression, stray loss per machine equal to Wt minus W copper divided by 2. And stray losses, which include the mechanical losses and the core losses, can be equal for both the machines when mechanical losses and iron losses both are same. So mechanical losses are same because both machines are running at the same speed, and the core losses or iron losses can be same if the flux in both the machines is same. So flux in both the machines will be same when the field current in both the machines is same. So in order to flow the same field current from both the machines field windings, we have kept the field coil of the generator at the motor side, right? So the same current is flowing through the field windings of the motor and the generator. So the flux in the motor side and the generator side will be same, and as a result, the iron losses in both the machines will be same, and then we can apply this expression, right? So we don't have to specifically or explicitly calculate the stray losses in both the machines. We will just measure the input and output powers, and then we will just calculate the total losses. Then we will calculate the copper losses. It is easy to calculate the copper losses because calculation of copper losses only requires the ampere meter, right? So by means or by using only 2 voltmeters and 2 ampere meters, we can calculate the total losses and the copper losses. So these stray losses can be evaluated by subtracting these copper losses from the total losses, and we can assume that the stray loss per machine is equal to total stray losses divided by 2. And this is possible if the mechanical losses and the iron losses in both the machines is same. So if the stray losses are equal to 150 watts, then we can say that 75 watts are the stray losses in the motor and 75 watts are the stray losses in the generator. So I think that was a good explanation for you, and that was explanation of why we have connected the field coil of the generator at the motor side. So in the laboratories, if you have visited the laboratory and observed these DC machines, these field winding circuit is separate, the armature winding circuit is separate. It is up to you whether to use that machine in separately excited mode or self-excited mode. And in self-excited mode, you can use the field and armature windings either in series or parallel. So that will become either series bound DC machine or a shunt bound DC machine. So similarly, if we have both machines, we can couple them, right? And we can screw them together over here, so they will be fixed, their output shafts. And the field winding of the generator can be connected in series over here, because this field winding of the generator is separate, armature winding is separate. It is up to you how to do the connection of these field and armature windings. So that is all about our today's lecture, and I hope you have understood the concept of field test in series bound DC machines. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.